familiar with it. The Manning's roughness coefficient N, I'll show you on the next slide what those values might look like. But make sure you use this with consistent units. Q in CFS, A is the cross-sectional area in square feet, hydraulic radius in feet, and of course slope is dimensionless. Typically they give you slopes like in feet per mile. Make sure you make that dimensionless like feet per feet. Those are some of the little things you need to be careful about. Now, here's the Manning's N for different types of, in this case I've given it for open channel systems, but you can imagine, remember that when you use closed conduits in stormwater management systems or urban stormwater systems, they also are made from similar materials. Like for example, finished concrete or unfinished concrete, Manning's N is 0.012 or 0.014. If they don't give it to you typically for concrete, I use like 0.015. Here's one for cast iron, riveted steel. You can see it's a little rougher. The higher the Manning's N, the rougher it is. For gravel type of system, channel, it's 0.029. So these are very, very approximate table. There are better tables in my references that you can use to get better handle on Manning's N. Anyway, once you get all that information, here's the method. The analytical method I will not do here. I've given you an example in the appendix. I would suggest you use the design chart again. So we'll go over that process. There's a separate chart like the critical depth. There's one for determining the normal depth also. Typically, this chart will give you the normal depth Yn. We call it Yn, by the way, unlike the critical depth Yc. Basically, it requires a dimensionless number, AR to the power 2/3 divided by B to the power 8/3. Remember I mentioned about AR to the power 2/3. That's called the section factor in uniform flow. And the reason I'm dividing by B to the power 8/3 is to make it dimensionless. So I'll do this through an example. Before I do that, let me show you this chart. Again, this chart is similar to what we saw for the critical depth. By the way, I did all these extra things for this graph to make it look better, because all these additional markings were not there in the initial graph. So this makes it a little bit easier for you to read or use. If you can print it out, you can. I'm sure they don't allow loose materials, but otherwise you might have to take it as a book, in the form of a booklet or something. Some of your review manuals may already have this. But anyway, we'll do through this example, but before I get to that example, just in this particular figure, there's only one horizontal axis. There's nothing on top, like we saw in the other case. And in this case, everything is for circular and rectangular and so on. So there's your rectangular pipe cross-section. There's your circular pipe. There's also for trapezoidal with different side slopes. Let's look at an example and I'll come back to this, how to use it. So in this case, I have a trapezoidal channel. They'll give you a trapezoidal channel, the bottom width, side slope, Z of 2. By the way, the side slope in some references might be referred to as small s. Be careful. But it's basically Z horizontal, 1 vertical. That's what it means. And that's what I've shown you right here. Z is 2 to 1. Okay. So for every 2 feet across, 1 foot vertical. So that's Z. In this case, is 2. S naught is 0.0016. This is the longitudinal slope, by the way, of the channel. That's the Manning's N. I'm going to give you that value here. It carries a discharge of 400 CFS. That means if a channel is carrying 400 CFS with this slope and this roughness, what should be the depth? Okay, and that depth typically is what we call uniform flow depth, Yn. By the way, every channel tends to flow at that depth. That's why it's called nominal depth. Basically, it's saying that there's something called abnormal depth, and that basically is any other depth other than normal. And I won't get into that topic here. That's too advanced for the morning session. It's often referred to as gradually varied flow. But anyway, for this particular example, we're going to do the simple uniform flow depth computation. So the first step is to calculate the section factor AR to the power 2/3 from the Manning's formula. So I've rearranged the Manning's formula to bring all the knowns to one side. In this case, Manning's N, Q, divided by 1.49 S naught to the power of half. All that information is either given or you can get it from other sources. In this case, 0.025 is Manning's N, Q is 400 CFS, 1.49 times the slope to the power of half gives you a section factor of 167.7. Make sure you do this calculation accurately. A lot of times you forget to recognize that this represents AR to the power 2/3. And so when you calculate the dimensionless ratio right here, use the number as is. Do not take to the power 2/3 again, okay? And that's a mistake very often people make, is in computing this dimensionless ratio, they forget that this number, 167.7, already represents AR to the power 2/3. So in this case, basically AR to the power 2/3 divided by B to the power 8/3 is 0.0569. And for this particular side slope channel, I'll go to now slide 68. For this ratio, I will compute Y over B ratio, just like we did for the critical depth. But keep this number in mind, 0.0569. I'll go back to the previous slide here. 0.0569 is near 0.06 right here, right near this vertical line. So I'm going to go up that vertical line, basically going over 0.06 approximately, to the curve that's labeled Z of 0.2, somewhere in the middle there. And if you go across, I'm somewhere in this Y over B ratio is between 0.1 and 0.2. I would say around 0.15. So, and that's basically what I have here is 0.168. And you can be a little more accurate. I'm just doing this as a demonstration here. And therefore, the normal depth is Y over B ratio times 20. B is, bottom width is 20 feet. Will give you 3.36 feet. So that's how you calculate the uniform depth. Now, by the way, they might ask you further under this uniform flow depth, is the flow subcritical or supercritical? Remember, we talked about the Froude number. So using this depth, Yn, you can always calculate the Froude number for any depth as V over square root of Gy. Velocity divided by square root of G times Y. You just use this depth instead of the critical depth. The Froude number will come out less than 1 if it's subcritical depth. If it's greater than 1, it's supercritical flow, okay? That means the depths are small, velocity is high. In this case, the depths are high, velocity is small. And that's an important thing to consider in most channel design systems. The reason that's important is most people don't like to design channels that carry flow with a very high velocity for safety reasons. Of course, at the same time, they don't want channels that are too deep, and therefore subcritical flow also you have to be careful when you design that. Now, before I go to some of the questions that are there in the chat box, let me just I'm going to set up a problem for you. Please solve this. In this case, how to calculate critical depth and normal depth, and of course the state of flow also. So make sure you do work this problem through. Good luck on the PE exam. And there are some references that I've included. The most important one is this by Chow. I heard it's back on print. If you can get your hands on it, either through your employer or wherever, please get hold of it. He does some of those graphs are clearer in the book. It's for open channel system. For water supply or pressurized pipe system, this Wiesman's book is pretty good, water supply. I've got some additional material there. By the way, here are the answers to those problems I've set up. So try these problems, see if you can get these answers. If you still run into a problem, I'll be happy to share the detailed solution with you. There is a loop system I've included for those who want to review this called the Hardy-Cross method. So you can go ahead and do all that. Let me look at these detailed questions that some of these things I was asked. I'm sorry about this, but what happened was that my chat box I thought was nobody was answering or coming through, and unfortunately that wasn't the case. Where did you get the 1.05 from? One gentleman asked. I don't remember. Is that from, you're talking about one of the 1.85? Oh, that is the exponent in the friction loss eddy equation, HF kq to the power 1.85. Well, that's an empirical equation for Haas and Williams, so it's just basically from experimental work. It's not something that you can derive it, okay? Just you have to go work with it. Okay, that's for, he's asking for basically the exponent in the friction loss equation H of F, which was, if you recall, going back to, I think those slides, quite a few slides back. And that's basically what he's referring to, I hope. I'm assuming that that's the case. Yeah, here it is, this equation. Basically, this for Hausen-Williams, if you remember, we talked about head loss equation due to friction as kq to the power x. Basically, one of the participants is asking, where do you get this 1.85 from? I can get for the other method, the Darcy's equation, I can get the 2. I can derive that, but not for this. This is empirically based method, and therefore it comes from the derivation of the velocity, by the way. I don't want to get into the detailed derivation, but if you basically manipulate for the head loss from the velocity, you'll get the exponent of 1.85. Now, if you go back to the previous slide on this, for the Darcy's-Weisbach method, there the x was 2. Now, this one I can get because if you remember the velocity for Hausen-Williams, for Darcy's-Weisbach equation, is V is equal to F friction factor F L over D V squared over 2G, and that's equal to the head loss due to friction. Head loss due to friction is equal to in terms of velocity, but you can always express in terms of discharge. And if you invert it, you can manipulate that equation to get it into this form, and there you'll see the exponent is 2 because it's V squared over 2G. So that translates into Q squared over 2G A squared. All right, let's see the next question here. Where do you find X in the friction equation? That's the same question I think I just answered. Next one is reservoir. If they give you P on the surface, is the pressure head P over gamma? Yes, that's true. What I said in that branch system problem, let me go to that slide. I'm sorry about this, but we got a few minutes to answer these questions. I apologize for not looking at the chat box as it should have. But anyway, in this case, let's say, for example, for this reservoir here, they give you a pressure instead of being 0. That means it's not a free surface. It's like an elevated tank. In that case, P over gamma is not 0, but it's equal to whatever the pressure in PSF divided by a specific weight of water, which is 62.43. So get that in feet and then add to Z1, okay? So in this case, my example, I'm saying P1 over gamma is 0 because it's got a free surface. Okay, let's move on to the next question. Can you explain the note? This is, I'm not sure which one this is. Can that gentleman maybe send me an email about the note? I'm not quite sure what note he's referring to. Next one is, how did you get ZJ of 20? Is that basically is referring to the same slide, I'm assuming? So let's look at this problem. I think he's referring to this junction. I'm assuming a hydraulic head in junction J as 20, and therefore, in that case, remember, I'm not assuming ZJ as 20. This one is the combined value of P over gamma plus ZJ. It's not ZJ by itself, okay? Because the J is an internal point, its pressure is not 0. While as for the reservoir point, P1 over gamma is 0. Therefore, Z1 is equal to whatever that 30 meters is. So that's 30 meters represents the elevation head, but not this 20. That 20 is the combined hydraulic head. Is that okay? All right. Does it matter where you pick the head of J? Can it be below? No, not at all. You can pick any point. In my case, I picked one above, one below. All you have to do is 2 trials, okay, in this problem. Seeing comments come in really late. What is this? I don't know what this means. Serious log. Is that yours? Okay. Is the critical flow part of Manning's exam on the exam? Well, it could be because critical depth is a very important depth in many open channel flows. Most hydraulic courses that we teach, I do cover some open channel hydraulics as a part of that first course in hydraulics. So I would expect similar questions to come on the exam. Is it faster to just check all the answers to see which gives root number equal to 1? I'm not sure which one you're referring to, but I don't know if that's a good idea. Oh, you're talking about if I gave you a depth and asked you to see if the flow is critical or not? Yeah, that might be one way to do it. If it's basically one of those multiple choice type things. Continuity equation for, this is the next question for pumps. I've seen that is a number of references for the exam. Continuity equation for pumps. Basically, I don't know in what context you're asking me that question. Um, can you email me a little more? I'll elaborate on that. Okay. Here's another question, slide 57, step 2. Where does the b to the power 2.5 come from? That's a totally arbitrary choice. I think I mentioned that. That's to make it dimensionless. Let me go back to slide 57 for a minute. He's referring to, I think it's further down this way. It's under critical depth. Yeah, slide 57. Okay. This b to the power 2.5 that he's talking about is essentially when I make it dimensionless, this guy right here. Remember ZC, the units of ZC are such that you have to take the bottom width to the power 2.5 to cancel the units of ZC, okay? You can work it out, look at the dimensions, and turns out that when you raise b to the power 2.5, it makes that ratio dimensionless. That 2.5 is just for that purpose, no other reason. Next, it says isn't slide 62, I'm not sure what that question is though. What about slide 62? Somebody's saying isn't slide 62. Let's go to 62 for a minute. Yeah. Does this participant elaborate on what he wants to know about this slide 62? I don't have in my chat box, I didn't see the entire thing. I don't know if I'm reading the whole thing or not, but it seems to be incomplete, that inquiry. Anyway, you can send me an email if you want to know more about that. Can we take the study material in a three-hole binder? You might want to ask the PE people that or ASC people that, but I think it cannot be in a three-hole binder. I think it has to be bound solid, if I'm correct. A hardy cross method for afternoon session only, usually yes, but they might give you a simple loop problem with a simplified thing. All you have to recognize in the morning session is the sum of head laws around a loop are equal to 0. So they could give you that configuration as a part of a hydraulics question. Is the Hardy-Cross method on afternoon principle possible in the morning session? I just answered that in a very elementary way, probably. What about as well as Appendix B, afternoon only? Not all of it. I put some basic analytical method of solving for critical uniform flow depth. Most likely analytical methods, I don't think they allow you to take calculators where you can use them to solve trial and error problems. So if you're going to stick to the graphical method, you probably won't need to do that. On slide 64, would you refer to slide 68? Is this reference correct? Let's go to slide 64. Okay. One of the participants saying I'm referring to a slide 68 with that side slope. No, this should be, thanks for pointing that out. That is, I'm referring to is the graph, which is slide 62, yes. So please make that correction. Thank you for pointing that out. That should be slide 62, and I'll make a note of it too. What is the alpha in equation 25? That takes me, this alpha is the kinetic energy correction factor. I think I talked about it. As far as you guys are concerned for the morning session, they'll either give it to you, if not, just assume it's equal to 1 in the equation. It's meant for the fact that you're using average velocity and to correct for the kinetic energy transported under those conditions. That's what it's intended for, okay? Where was I? Let's see. Do you know where I was with alpha? Okay. I'm trying to see where it was here, and then we'll quit here soon. Okay, as well as Appendix B, I've answered all these. Yeah, I've just answered this one. Next one is, what this says is, Oh, no, I lost that. Okay.